In example 1 here, we're going to be asked to take a look at the cardioid that's given by 1 plus sine theta and find the slope of the tangent line that would exist out at this point. Notice again, this here is a polar point. This is going to be my angle theta and my value of r. We want to find the slope of the tangent line. We don't even need the full equation, just the slope. Now, I've already gone ahead and went to my calculator and brought up the following picture. Here's the picture of the curve that I'm looking at. And I can kind of probably imagine that, well, if I was to rotate pi over 3, that might, that's a little bit more than 45 degrees out. So maybe that would point me, I don't know, maybe like up in this direction here. And if I walked out to the curve, I would be somewhere around this point. And I can imagine a tangent line that would extend over this. Right, some tangent line is going to rest on top of this here. And it looks like it's going to have a negative slope. So I'm going to expect that my answer should be negative. So if I want to go ahead and compute this, I need to go ahead and set up my derivative calculation from the previous theorem. But before I can do that, I need again to parameterize this polar curve. So I'll say we see that if x is equal to r times the cosine of theta, and y is equal to r times the sine of theta, then I can kind of update these by replacing r with the formula that r has, which is 1 plus the sine of theta times the cosine of theta. And then down here, 1 plus the sine of theta times the sine of theta. And so I've now parameterized my polar curve into this parametric curve. So I can now then calculate that if I wanted to find my dy dx, I just have to do the derivative of y with respect to theta over my derivative of x with respect to theta. And that's not actually that difficult. So let's see, I'll start with the derivative of the y. So I'll start by saying, well, let's see, what's 1 plus the sine, and that derivative would be cosine of theta. And then I'll leave the sine theta alone, and then I'll reverse the order. I'll leave the 1 plus the sine theta alone, and I will take the derivative of the sine, which is cosine. Perfect. I'll do the same thing in the denominator. I'm going to end up with a cosine of theta and leave the other cosine alone. And then I'm going to leave the 1 plus the sine theta alone. And the derivative of the sine, or sorry, the cosine there is a negative sine theta. And so I'll put a minus out here in the front. So this is a crazy formula here for the derivative. And I don't even actually have to do much with this particular formula. I can go ahead and just quickly see that what I'm interested in doing is evaluating this formula at the given angle of pi over 3. So we want to evaluate dy dx at theta is equal to pi over 3. So let's see what we would get. dy dx evaluated when theta is a pi over 3. I'm just going to start filling in what I know for these different trig values, or trig functions at pi over 3. I know that the cosine is going to create a, oh wait, not a square root of 3 over 2, that should create a 1/2. The sine will create a square root of 3 over 2 though. And then I'm going to have a plus, and I'll have 1 plus the sine is going to be square root 3 over 2. And that is multiplied by a half. If I was to go ahead then and consider what I end up with in the denominator, I end up there with a cosine times a cosine, so that's a half times a half. I'm just going to write that as a quarter. And then I have minus, and I have 1 plus my square root 3 over 2. And then my sine theta is again another square root of 3 over 2. So there it is. That's the slope that I have for that tangent line. Now remember, based on the picture, we expected this slope to be negative. So I'm going to go ahead and simplify this down just to confirm that I do indeed get a negative value. Let's see, in the numerator here I get like a square root of 3 over 4. And then I get a 1/2 and a square root of 3 over 4. Okay, in my denominator, I'm going to get a 1/4 and I'm going to get a minus. I'm going to distribute this negative and the square root of 3 over 2 in at the same time. So I get a minus square root of 3 over 2, and I'm going to get a, let's see, a minus 3 over 4. So a minus a 3 over 4 when I multiply this square root of 3 over 2 to the other square root of 3 over 2. Now if I simplify this down just a bit more, I'll see that in the numerator I get square root of 3 over 2 plus a half. And in the denominator, it looks like I'm going to have a negative square root of 3 over 2, and ultimately, minus a half. Oh, wait, so top and bottom are actually almost the exact same value. It's just the denominator is multiplied by a negative, so this simplifies down to negative 1. The slope of our tangent line here is negative 1, which is perfectly in line with the intuition we had that the slope should be negative. Notice that this process isn't supposed to be difficult by any stretch, as long as I understand how to do this first piece, which is to parameterize that polar function.